Today we have with us, as part of Database Week, a really super special speaker. We have with us someone with 30 plus, no, not 30 plus, nearly 30, right? Over 30, cool. 30 plus years of software and technology experience. He's one of the early architects of Objectivity DB. Please welcome the VP of Product Management for Objectivity, Brian Clark.
Good evening, everybody. Can you hear me okay at the back? Yeah. So, I'd like to thank the hosts, and they actually put this on. When I walked in this evening and saw the red telephone boxes back there, I immediately at home. I don't know how they do it. I thought that's right.
You're okay.
I go to quite a few of these events, and I always wonder about the person up front that's speaking. What the hell does that person before I start asking questions? Sorry, how's that?
Much better.
Okay. So a little bit about my background. Eric sort of said 30 plus years, and I'll tell you how I got into computing. But first of all, when I first went to school as a little lad, they kept talking about the 3 R's: reading, writing, arithmetic. And I looked at this and I thought, hang on, that's not 3 R's, it's an R, a W and an A. And I knew I was in trouble. So I actually got through school, went to university, and this time it's the 3 B's that got me. Bands, Friday night dances, I ended up organising the Friday night dances. The booze, I like my beer. In England, we call the girls birds. Not quite sure what we call them over here. But it was the 3 B's that got me. And guess what? I knew I was in trouble. But by this time, I'd actually got to know some people in the university, in particular the Professor of Applied Maths and Computing, and the department head of the Computer Science Department. And I got thrown out because I've been visiting the 3 B's. And they said, what are you going to do? I said, I don't know. And so they said, well, do you want a job on the university computer? And I thought, well, better than nothing, so I took a job as an operator. And this was in 1970. That gives some idea about how long I've been around doing this stuff. And so my first job was on this mainframe. It had 64K of memory. And it had 2 spinning disks, 8 megabytes. And the computer took from here way back to the back of the room. Okay? And if you think about it on your laptops today, you know, gigabytes of memory, terabytes of disk. So, you know, a lot's happened. And one of my jobs as a mainframe operator was actually to process the batch jobs going through for all the students and research guys in the university. And they wanted a turnaround as quickly as possible. My goal was to do get as much through the computer as possible through those scarce resources as quickly as possible. So maximise the use of scarce resources. Think about today, or with grid computing, trying to make use of the scarce resources, get the work done. I had a selfish reason, because I was on shift. If I got the work done, I could go home and go down and home. But if you look at what happened over the years, then really it's all been about getting the most out of the scarce resources that are the computer resources. And similarly, if you look at databases, then back in the 60s there was a hierarchical model, IBM, network model, the code cell databases, IDMS. Then along came the behemoth of the relational model. People like Oracle, IBM, Microsoft, they all got their relational models. Then in the 90s, the object databases came out. And although some of us really weren't there as object database people to take over the world, some of the other guys really thought they could take away from relational, but it didn't happen. But if you look at what's happened in the last 10 years with the NoSQL movement, people are finally realizing that relational databases, one size does not fit all. You need to choose the right technologies to do the job. So Objectivity, the company I work for, that provided this wonderful stuff that we've just given out, and I just feel exhausted from watching Eric throw all this stuff around. But we have two products, the original Objectivity DB, which is the object database, and then more recently InfiniteGraph, which is really a graph API around the object database, the traditional product. And Objectivity has been around since 1988. I joined at the end of the first year, so 23 years. And I attributed that to being European, we're lazy. We don't like changing jobs, so we stick with the same. Despite the accent, we're actually an American company based in Sunnyvale. As I say, we've been around a long time, got some good customer base on the Objectivity product, and we also have looked at the graph technology and where the graph databases fit in. So we're going to talk about big data and NoSQL. There seem to be buzz phrases these days. You've probably seen some of this. We all know that the data size is increasing. And this is a quote from Eric Schmidt. So every 2 days we create as much information as we did right up to 2003. So the volume's increasing, and it's increasing even at a faster rate. If you think about it, I'll keep talking about graph databases and graph data. In my mind, graph data is all around us. I mean, how often do you walk down the street and actually see rows and columns of tables in the world around you? It's really all about objects and relationships. So if you think about social networks, social media, Facebook, it's all about people and relationships. Well, that structure is a graph. People know people know people. People work for organisations within organisations. So it really is, there's a lot of graph data out there that we tend not to think about as graphs because we've been told data is rows and columns of a table. Nowadays there's sort of more unstructured data. An example could be a video, although I would argue that even that is structured. And then there's a lot of combinations, heterogeneous combinations of structured and semi-structured data that needs to be handled whether you put it in one database or different types of databases with relationships between that data. So you need ways of storing these different types of data. And then the other thing, we'll see that with the Objectivity database, it really has always been about distributed data and distributed processing. Then with the service-oriented architecture these days, we're building much more distributed systems, distributed processing and distributed data. A couple of quotes I just picked up today. I won't read them out, but people are beginning to realise now the importance of graph data and the representation of the graph and the types of queries. During the questions, somebody mentioned market research as an example. The sort of things you can do is, with traditional data, people buy products from a website, then you can find out what a person bought, and also what are the products that they buy. But if you want to start asking questions like, this person bought this, who else bought this, and what else did they buy? Then those sort of queries are hopping about doing navigational queries, which is not so easy to do with a relational database. But when you get to some of these complex graphs, you actually need a different structure than a relational database. So I think I'll be able to go through this portion of the slides fairly quickly. Eric did some good questions on some of these topics. And so there's 4 different types of the NoSQL technologies: key value stores, pivot-table clones, document databases, and graph databases. And InfiniteGraph, our graph database product, is actually built on the core technology of Objectivity DB. And we put it in there because Objectivity DB is a fully distributed, scalable database. Distributed data, distributed processing. So in terms of complexity and performance and scalability, we're right up there in that top right quadrant. So again, I updated the slides today. This is where Eric got a lot of his good information from. So we'll leave them in the presentation, but I'll just skip over unless you have any questions. Eric? So anyway, the video of the presentation will be made available afterwards, so always get to the material. Okay, so mentioned earlier that there's all these different technologies, and you're no longer in this world where a relational database is the only tool, one size fits all. You have to choose the right tool for the right part of the job. And so the relational databases, they still have a place, we're not going to replace them. The different NoSQL and not only SQL technologies still has a place. And so you have to choose the right database for the job. We'll look at what the object databases and graph databases and the types of problems they help solve.
What's the main point of the first slide? Like the one or the first one, the one before that. Basically, you're saying the relational database still have
Yeah. If your data fits neatly into rows and columns of the table, why not use a relational database? They store data and process data. So let's take these questions offline. Okay, so big data, during the questions we talk about volume, velocity and variety. What I say is it's all very well being able to take in this volume of data in high speed, rapid velocity, and the different types of data. But once you've taken it in, once you've ingested it, if you don't do anything with it, if you can't do anything with it, what's the value in it? So it's not just capturing or ingesting the data, it's being able to process it and get value. And then there's a lot of talk about Hadoop these days. Everybody sort of thinks it can do everything until they try and fails. So it's good at what it does. But if you look at the features, MapReduce is about distributed processing. Objectivity and InfiniteGraph, we've always been about distributed processing. HDFS, distributed file system. InfiniteGraph and Objectivity, again, distributed data. And remember, we've been doing this stuff for 20 years. Before big data was big data. Before NoSQL was NoSQL. As I say, there's a lot of talk about big data. If you look at the sort of architecture of some of the solutions, then they're trying to deal with structured, semi-structured, and unstructured data. So there's different data stores. You need to ingest that data very efficiently, very fast, and then get value out of it by applying analytics and visualization tools. And what we're seeing is that the big guys in the space, people like IBM, Oracle, HP, EMC, are all coming up with their own big data architectures, but they're all following a pattern, which is the observe phase, which is the getting the data in, ingest data, some front-end processing. Typically that's going into a Hadoop or a Hadoop-like system. From there it's processed, analysed, MapReduced in parallel, and generates data for other stores, including relational databases. And then the various analytics and visualization tools operate on that and provide value. And in Objectivity, we've always classified some applications as MARS, which is Monitor, Analyze, Respond systems. A few weeks ago, I was looking at some big data terminology in a paper, and they've actually got a new way of describing it, OODA. Observe, Orient, Decide, Act. It's just the different stages that the data goes through. If you look at, say, what the big guys are doing, we're all following this pattern. Which is good, it gets the data in, it gets value out of it by applying analytics. But you still end up with data in different silos in the database. And what we believe is that in these silos, there's relationships in the data, hidden in the data, that's not being used. And so, for instance, if you had a, say, an airline booking system, a reservation system, you would know what people are going to what locations and what time. If you had a terrorist suspect list, then you know who the bad guys are and how they work together. If you've got a geographic database, you'd know something about the locations. So if you combine those three different silos of information, you can start asking questions that, we know this person is going to this location on this day. Who of his associates are travelling near that location at near that time? And that is a graph-like query. So being able to discover the hidden relationships in the data and then physically persist those relationships, then you can do very intelligent queries across those relationships. So Objectivity, InfiniteGraph, then it's all about the objects and relationships. Somebody was asking, what is a graph database, what is graph data? And it really is objects and relationships in graph terms, nodes or vertices and edges. A good example is a social network. People know people, know people, know people. So, going back to what I was saying earlier, that we're not going to replace relational databases, we're not going to replace any of these. And the idea again is to help discover the hidden relationships, then be able to persist them, and then use that graphic data to do different type of navigational queries. How are things connected? We believe that these two people are connected in some way, but how? So it's the old Kevin Bacon, 5 degrees of separation. So with a graph database, you can take any two objects or nodes and say, give me all the paths between these two people. Or a question like, what is the shortest path? So social networks, somebody was talking about security, money laundering, for instance. Money doesn't go direct from A to B. It spreads out, and spreads out, and spreads out, and then comes back together again, and converges. So again, if you can plot that, the route of the money, where it goes when it comes back, you can find out all the individual steps involved. So what is a graph database? It's optimized about the relationships. We call the relationships of first-class citizens. So it's more than this thing points to this thing. It can actually have properties. So even in a social network, the fact that I know somebody because I work with them is a different type of relationship to I know somebody because they're family, or I know somebody because I met them at a meeting. So those relationships have values, have strength. The graph database then, we're dealing with nodes and edges, so it's a very focused, small API, deals with the vertices and edges, and navigation of the graph, which is probably the key query component. And so it's typically not SQL, because there's no real navigation statement in SQL. Graphs grow quickly. So one of the examples we'll look at later is some work we did for an intelligence agency where we analysed telephone call records. Okay, everybody's claiming to analyse telephone call records because they're flat. A calls B. But then if you build a graph of who called who, then you can start asking those questions that we're interested in this guy, he's a suspect, and we're interested in this guy because we know about him, and you can find out what are their connections, how are they connected. So if you think about the number of phone calls even in the US, billions a day. So being able to build a graph, not just a snapshot, but an ongoing graph of this data and who's calling who is very important. So the volumes, remember about big data volume is very high, velocity is very high, and the variety. So people don't just communicate by telephone, they communicate by emails, by text messages, by social media. So there's lots of different ways that people communicate. So again, that's the variety. Now, if you think about how data is represented in a relational database, rather than columns of a table, then if you wanted to do the sort of graph-like query, it actually results in a many-to-many join or a recursive join. Once you get into some of these graphs, traversals, where you've got millions of nodes and edges, and then trying to do a recursive join across that data becomes a pain. If you haven't tried it, I'll show you some results that we run. In the graph world, in the object world, we actually represent these relationships like in-memory pointers. They're actually persistent pointers in the database. And so when we come to traverse navigate the graph, we're following these persistent like pointers in the database. So it's very fast. Okay, so here's some results of some tests we did. It was in the early days, but before we actually built InfiniteGraph. You know, we knew about objects and relationships, and we had a lot of customers doing things with objects and relationships, but we weren't really comparing ourselves to graph technology and how relational databases would try and do the query. But we knew we were good at doing these traversals, these navigations. So we did some tests, and this first one in red, then the actual number of nodes and edges in the database was 640, so 640 rows in the join table. And you can see that even at 100, it started having problems with the recursive join. This one did a little bit better. It actually managed to go up a few more. We were waiting 2 days for a result. And then these other two, again, they went out further, but still tailed off. And those numbers, if you think about having millions of telephone call records and traversing a graph like that, then you're dealing with millions or billions of nodes and edges. Look at what these guys are doing. So again, I'm not here to knock relational database technology. It's good at what it does. But for this type of problem, where the data is graph-like, lots of connections, then you need a different technology. So InfiniteGraph is built on top of Objectivity DB. This, if you like, is the Objectivity DB engine, distributed database. And then these are the plugin components into InfiniteGraph. And the idea here is that you can actually, as a developer, modify the behavior of the database by these plugin components. InfiniteGraph's the core API. It's 10, 20 classes, 100, 200 methods, compared to the Objectivity, which is hundreds of classes and thousands of methods. So it's a limited API. It's all about graphs, nodes, edges, and traversals. In the graph world, the NoSQL world, open source community, very, very popular, very prevalent. There's an organisation called Tinkerpop. They have a stack of solutions. The Graph API is actually something called Blueprint. You could think of Blueprints as the equivalent of ODBC for graph databases. It's an open source effort to attempt to provide a standard API, a standard way of accessing any particular graph database. So we've implemented the Blueprints interface. Then our users, our developers, develop in Java, use the Java API. So we support distributed parallel ingest. We've got to get the data in quickly, and get it in parallel. Distributed storage, we can spread the database across any number of database servers. You need entry points, start and end points for the graph when you're doing the traversal query. So we provide node naming and indexing for fast lookups. The navigational queries I particularly like. It's all very object-oriented. And so the navigator is an object. How many of you are familiar with OO languages? Java, C++, C#. Probably about half, and probably about the same people that are the NoSQL people as well as the relational database. So for the navigator then, if you think about traversing a graph, you've got nodes, which are the objects of interest. So it could be people, it could be people of different types, professional people, engineers, accountants. They could have different relationships to each other, which would be the edges. So when you're traversing the graph, you need to qualify the navigator. And so you can qualify on the edge of the relationship, the type of the relationship, and any properties on that relationship. So you could say I'm looking for people I work with, my colleagues, that are under 40. So you can just qualify that you go down paths that meet that criteria. Once you get to the next node, then you're at an object, another person, you then want to qualify that. So as you're navigating, you can qualify as you actually, we actually perform the navigation. And these qualifiers are objects as well. So the navigator is an object. You give us an object, we start from there, we navigate, and the qualifiers are objects. So it's a very object-oriented approach. We provide a basic visualizer. There's other people who do better jobs than our visualizer. It really is just a basic visualizer, so you can look at the graph. There's lots of third-party tools that do visualization and analytics out there. So we partner with them. There's one in particular, I think we're on the East Coast, a company called Tom Sawyer. It's a visualization and analytics tool. So they've actually done an integration direct into the graph. The objectivity architecture, again, this is the core component, the core database component of Objectivity DB and InfiniteGraph. Then, yes, we are a client-server architecture. We have clients, we have servers, but they're different. So if you think about the relational databases and some of the NoSQL technologies, they still follow the central server model, particularly the relational databases. Which, as probably many of you know, that if that central server becomes overloaded, you replace it with a bigger server, a bigger piece of hardware. You go out and your bosses or your accountants buy you a bigger machine. So that's a replace strategy. In a distributed world, and this is true of Objectivity and the NoSQL technologies, you have a sort of an incremental scale out. So if you need more database server, data processing, you add more data servers. If you need more client processing, more applications, you add more client servers. So it's a scale out. But we do have servers like the log server, that's for concurrent access to the database. We talked about transactions, ACID earlier. That's handling concurrent access. Paid server is a remote server. So if we've got a type application accessing data from a distributed location, a remote location, it would actually talk to the paid server. And then the query server, think about distributed data. Rather than bringing the data to the query, wouldn't it be nice if you can actually spread the query out, send the query to the data? So we can actually do that, the query server. The Objectivity kernel, that's the guts of the database. Access through a C++ API. So the kernel is actually written in C++ for high performance. Then we provide other APIs, Java API, Python, C#.NET. And we also have through ODBC, you have a relational database SQL access. And then the user application can be written in any of these languages. So if you think about distributed data and processing, then distributed data anywhere in the network, across many servers. Some of those servers could be just data servers. Some of those servers could actually be running applications as well. So it's distributed data, distributed processing. One of the things we talk about a lot is the scalability of a database. So in Objectivity, the database is not a single file. Think of the database as a federation or collection of database files. Then those files can be spread throughout the network. That gives us tremendous scalability. Even 20 years ago, we were thinking 64-bit. So we had a 64-bit address in the database for the objects. And then that gives us the 64-bit broken down to 4 16-bit IDs. Database container is a subdivision of the database for physically clustering objects together that are logically related together. And then page and slot. So anyway, that structure gives us over thousands of petabytes. It's actually millions of petabytes or yottabytes. If anybody wants to do the sums, they can. It's lots of zeros. And it's over thousands of trillions of objects. Now, some of the work we're doing with some of the agencies, we're actually getting worried about the 64-bit object ID. The object itself, yeah. The always represents the object, and you can give the object. Quite often you would build collections of these objects, and then find by the value of them. It could be social security. We talked about the distributed processing, talked about the servers. The other thing where we're different than traditional client-server architectures, if you remember the core component, the kernel of the Objectivity database, it's actually a library that gets linked inside the client. And just in case you're now horrified, think, well, my Oracle image is 100 megabytes or whatever. Our kernel library is about 2 megabytes. So it's not this big hunting server, it's a small library with just the necessary pieces of the database. So then you have multiple clients anywhere in the network with their own database knowledge, if you like, their own database kernel, can access database servers anywhere in the network. So that gives us this fully distributed peer-to-peer capability. Working in this distributed environment then, got the opportunity, we've got lots of different APIs, so you can mix APIs. So within a federation, which is a collection of databases, you can have high-performance ingest applications, say written in C++, and then a GUI application written in Java. Some database administrator wants to come and do some admin on the database, on the federation. He could write some tools in Python So they all interoperate against the same federation. And then in the world of distributed world of today, then we've got mixes of platforms, mixes of machines. So we've got Linux, Windows, different Unix, Mac. So you can store the federation, the different databases on different types of hardware. So it's heterogeneous on the hardware side and interoperable on the language side. And then, of course, we work with the SANs and the network storage. Okay, so this is an example then of some work we did for one of the agencies where we analysed the telephone call records. So this is just an example using our visualizer of sort of the way the data is structured and what it would look like. Connections work, which appears to be, then this is linked back to one of our servers where we're actually running this demo application. Any? Yeah.
See that in the back? Did I ruin it? So good?
Don't go too far. So in this database, we've got 10,000 people, 10,000 addresses, some businesses. The phone calls, what have we got here? 1.5 million. Not huge by any means. We can select a start and end point and start hunt. And this is going, searching the graph with the 1.5 million calls, and it's given a start point and end point, looking for all paths between. Step up the number of degrees of separation. Start again. And what you can see here is, as soon as we start finding paths, full paths between the two objects, the start point and end point, then we're returning results straight away. Okay. You're not having to wait for the result set to complete before you can start using the results. So in a very long traversal, say this is only 1.5 million calls, we're dealing with billions. So once we start getting results back, we can actually interrupt the stop the navigation. So you don't have to wait for the navigation to begin. This is just a rough view of front end that we've put on top of the application. Just start with 10 points. This is set to start at 10 past. Normally you just let it explore. Yeah, it really depends what you're looking for. So this is the sort of thing that intelligence analysts are really interested in. Looking at how things, people are connected. commercial organisation, so obviously there's a lot of good stuff on the web for you to access as a developer. Talked somewhat about that during the various questions about the different types of use cases. So sales and marketing, so somebody mentioned marketing, so grid research, network management, telecoms, another example of a network graph. Big one for us is this space, both with the original Objectivity DB product and now with InfiniteGraph. We're actually doing some work with it's a fairly new agency called the National Media Exploitation Centre. It's actually public, or this piece of it is public. Basically what they say, because in the past, and all the different agencies, if they discovered something of interest, like somebody's laptop, right, then they would take the data off that and keep it themselves. The idea behind the NMEC is that they would centrally collect all that data, then they have a big graph of everything that they know about anybody of interest. So if you're a terrorist suspect, you get a visit in the middle of the night and they take your laptop away, then that gets added to the pool of information. So they're talking about trillions of objects of interest, and just imagine the relationships. But that really does help them find the bad guys. We actually had a visit in Sunnyvale by one of the senior analysts in one of the agencies. And until that visit, he uses this tool every day of his life. He didn't know that Objectivity was inside and was enabling him to do his job. So this was the demonstration I was showed, the real work we did for an intelligence agency. So for the test data, we had 400 million calls. And they wanted to find the links out to any degree of separation. And they've been trying to use Oracle for this problem for a couple of years. And the best they could do was set up a query at 4 degrees of separation and extract a result in 40 hours. We were able to build this on somebody's macro. And we were returning, remember I said we return results as soon as we find them. So we were able to start returning results in seconds. So rather than having to wait 40 hours for a result, we could start feeding them the information they needed in seconds. Yeah, right, that's results were unacceptable. Somebody once put it that if you wait 40 hours for a result, then you have to let the bad guy go. You can't keep him that. There's a type of application that get used in a lot called sensor fusion. So, these days, I'm sure they were talking about it in Chicago today, the UAVs, the UASs. And, the amount of data coming from the sensors these days, just like, big data, it's increasing in volume, velocity, and variety. So they collect all this information from operations, and they use systems built with Objectivity or InfiniteGraph to do what they call the sensor fusion. So the types of data is intelligence data called SIG-int or L-int or Q-int, different types of intelligence, and they bring it all together and use Objectivity DB as the database that helps them fuse it together. Then they can start asking the questions, how these things relate. What's interesting is, I'm not quite sure how many of you are involved in sort of any work with the system integrators to the government. People like Lockheed, Northrop Grumman, most of you are IT folks. So all these system integrators, people like Boeing, Northrop Grumman, Lockheed, they all have these sensor fusion engines. They all use Objectivity as the database inside them. So another one, this one's actually been deployed in Afghanistan, network-centric collaborative tools. So it's in live operation by the forces in Afghanistan. And again, it's whether it's ground or seaborne or air, then all the different sensors coming together and collecting or fusing that data. In the past systems, again, each sensor, the data was captured, but it was in a silo, and they didn't have sort of a single common picture across all the silos. So the fusion part is moving up all together. This one's an InfiniteGraph customer. They're actually building what was described as the Facebook for education. It's one or two guys out of Cyprus. They're using the free version of InfiniteGraph. It's limited to 1 million nodes and edges. You can download it from the website. He started building this. It's for students and teachers and courses, and build a social graph of that environment. And then, students can look for students doing the same sort of courses with the same interests, following them, get the same education. This one we found very interesting, web and mobile ad placement. So, I don't know whether any of you are sort of walking down the street and your phone goes, and you push a message saying there's this restaurant down the street, and it happens to be your favourite food restaurant. So this is what they mean by the targeted ad placement. So they know who you are, they know where you are, they know what time of day it is, and they will start pushing adverts to you. So if it's lunchtime, obviously you might be looking for a restaurant. So what food do you like? Chinese food. So they'll start sending you adverts or coupons for that particular type of restaurant. And we're actually seeing now that people that have been looking at this are generally startups, but now the telecoms guys are actually cottoning on that they own the network, where all this data is coming from. They know the location that's actually in the network. So they're looking at leveraging that information. Healthcare. This was an interesting one. We actually did a proof of concept with Objectivity. The problem is that as a patient, you go to the doctor and say, I'm ill, and he wants to prescribe some drug medication to you, but you might be allergic to an ingredient in that drug. And so if you think in sort of software database terms, it's sort of a many coming in from the drug side and a many coming in from the patient allergy side. Then trying to find that intersection in a relational database is not so easy to do. With the graph database, it's all paths between. So basically, is there a path between this patient through this allergic reaction to this ingredient? If there is a path, then you know the patient's allergic and they will prescribe that medication. Fraud detection, we talked about earlier. The idea that the money doesn't go from A to B, it comes out, comes back together. Yeah, that's the graph. So that's it in terms of the presentation. Before we go into the Q&A session, Eric's got some more. Thank you.